Look at the sheer footprint of this operation. To isolate a few pounds of valuable uranium, metallurgists have to process thousands of tons of useless desert rock. They engineer phase changes, forcing solid rock into liquid, manipulating it chemically, then returning it to a concentrated solid. This starts with physical force. Raw ore is wet ground in a rod mill into fine sand, passing a 20-mesh screen. But crushing only reduces the physical size of the rock. To separate the uranium trapped inside that sand, we have to cross over into chemical manipulation. This image shows the massive industrial tanks where the primary extraction takes place. Inside these vessels, the ground sand is mixed with sulfuric acid and oxidants, driving the pH down to a highly corrosive 1.0. This creates our first phase shift. The solid sand is no longer what we want. It is now waste. The highly acidic liquid dissolves the target uranium, pulling it completely out of the solid rock. The acidic mixture is pumped upward through a filter bed of steel shavings to reduce unwanted iron, and then passes through sand filters to strip out any remaining solid particles. What emerges is a clarified, highly acidic, pregnant solution. The uranium is completely isolated from the rock, suspended entirely within the liquid phase. We have successfully freed the uranium, but our new problem is that it is trapped inside a massive, difficult-to-handle volume of corrosive acid. This diagram shows how we concentrate the element. We pump the acidic pregnant solution into a series of mixer settlers and introduce a kerosene-based solvent. Because kerosene and water are immiscible, they physically refuse to mix. They stack into two perfect layers. The acid settles on the bottom, and the kerosene rests on top. Chemically, the kerosene solvent acts as a magnet. It possesses a much higher affinity for uranium than the acid does. This physically pulls the uranium atoms across the boundary line, locking them into the upper kerosene layer. The other dissolved minerals and impurities lack this affinity. They bounce off the boundary line, remaining trapped entirely within the bottom acid layer. By utilizing immiscibility, the uranium flawlessly jumps from a massive pool of impure acid into a highly concentrated, highly purified volume of kerosene. Let's pause and test our logic. If a highly acidic pH forces the kerosene to grab the uranium, what environment forces it to drop it? The answer is an alkaline solution. In a process called stripping, we introduce a 10% sodium carbonate solution. This reverses the chemistry, forcing the kerosene to release the uranium into the carbonate liquor. This simple reversal isolates the uranium in a third liquid. Because the expensive kerosene is completely emptied out, the plant endlessly loops it backward to extract more uranium. Now we force the final phase shift. The carbonate in the liquor is destroyed using acid, and ammonia or magnesia is added. This reaction forces the dissolved uranium to precipitate out of the liquid. We push this resulting slurry through a filter press. The liquid drains away, leaving behind a dense, bright yellow solid material known as yellowcake, testing up to 80% pure uranium oxide. This image documents the final physical output. The dense yellowcake is dried, packed into heavy industrial drums, and prepared for commercial shipment. The entire pipeline relies on these precise shifts: solid ore to an acid leach liquid, into a kerosene extraction liquid, transferred into a carbonate stripping liquid, and finally precipitated into solid yellowcake. Through this engineered sequence of chemical phase changes, thousands of tons of barren desert rock are successfully distilled into concentrated fuel.